Hello, good morning, everyone. Welcome to anticipatory briefing number 9 of this 2025 GESDA summit. We're going to talk about preventing the next pandemic. Emerging pathogens driven by viral evolution and the human impact are raising the risk of pandemics as climate change and habitat disruption accelerate. How will new insights into pathogen biology transform surveillance, diagnostic, and global health preparedness over the next 5, 10, and 25 years? That's going to be the topic of a 15 minutes presentation, followed by 15 minutes of Q&A with the people in the audience. Our speaker today, she's the director of the Center for Emerging Viral Disease, which is a joint initiative of the University Hospital of Geneva, known locally as the Haug, and the University of Geneva. She's also a committee member of the Radar 3.6 Pathogen Biology. Please help me welcome Isabella Eckerle.
Thank you very much. It's a great honor and a pleasure to speak at this summit. And I want to give you a bit of insights how we can be anticipating novel pathogens and maybe what we can do better for the future. So these guys are actually the reason why I'm standing here today and talking to you. Because when I was a junior doctor working and traveling in Africa more than 15 years ago, I became absolutely fascinated by bats. I came across them for the first time in the wild there. So these are straw-colored fruit bats in the botanical garden in Kumasi in Ghana, where I later worked and studied these animals and their pathogens. And bats are really unique. They are not only weirdly beautiful, at least I think that, but they are also the only mammal capable of true flight, and they have this amazing ability to carry a vast amount of pathogens without getting sick. So they carry pathogens like Ebola or Marburg virus, who are among the most pathogenic and deadly viruses in humans, up to 90% mortality rates for some of these strains. And they are unbothered. They just go after their life. So this recognition that bats, and in the meantime we know also other wildlife species, can carry a lot of pathogens, has led to almost a new research field that we call virus discovery. And that was started around 20 years ago, but it was also enabled because we have a powerful new tool that is metagenomic sequencing that has become better and better and better due to many advances in biotechnology, but also in bioinformatics, and it has become much cheaper. In theory, we can implement it globally. But this excursion, and of course a lot of pathogens were found, has also led to new questions, like which one of these pathogens actually has the potential to move into a new host to infect us, and which one will always stay an animal pathogen, never any relevance of us. And maybe even the bigger question, how can we respond to new pathogens before they infect humans? So let me give you some context. So this map is a snapshot, and really only a snapshot, of major infectious events of a little more than 4 decades. Every dot is a single event. Many of them you've probably never heard of, and others, they have changed our world. HIV in the 80s, the SARS epidemic in 2003, the pandemic influenza H1N1, also called swine flu at the time in 2009, many different Ebola outbreaks, a big one 10 years ago, one currently taking right now as we are standing here in the DRC with physicians of our center being on the ground helping to tackle this challenge. And many pathogens, we've never heard of them. So we only know of their existence the moment they cause disease in humans, they cause an outbreak. That are the ones that are truly emerging. But there are others that we call re-emerging. So we knew about these pathogens for a very long time. But we somehow didn't care, we didn't think they're relevant, they were in regions that didn't interest us, so we really neglected them. One example is Mpox, that was formerly known as monkeypox. So the virus was first discovered in the 1950s, human cases described in the 1970s, but actually it took until 2022 until this virus actually became global attention, only when a multi-country outbreak occurred. And there are other ones, polio, measles, they were once earmarked for eradication, but instead of eradicating them, cases are rising due to anti-vax movement, vaccine hesitancy, and just the complicated state our world is in right now. And there is also another one that is a single dot here, this black dot, and that we should not neglect. It's deliberately release of pathogen. It was the anthrax bioterrorism 25 years ago, but there are now fears that AI may help to easily design even pathogens or help people who are not skilled in the laboratory to release pathogens. And I think we live in a very fragmented, complicated world. We should not neglect that. So, but actually, where do all these pathogens come from? Over 60% of them, of all emerging infectious diseases, are zoonotic. Zoonotic means they can be naturally transmitted between a vertebrate animal and humans. More than 70% comes from wildlife. And there are an estimated 1.7 million yet to be identified viruses in animals. So that's a lot. And among them, there are, of course, some that can infect humans. So I hope you agree with me that this is a global and not a local challenge, and we need to do something to tackle this. But why is it so difficult and so tricky to get one step ahead of these pathogens? It is because we need to change our traditional way of thinking and teaching. When I was a young medical student, this is how emerging infectious diseases in a patient appear to me. There is this sick person with a weird pathogen seemingly coming out of the nowhere. But pathogens just don't come out of the nowhere in humans. They come from somewhere. And the reality is that this sick person is only a tiny piece of a much, much larger puzzle that we normally, being traditionally trained in silos, for example, in human medicine, in veterinary medicine, don't really realize. So many pathogens, and especially viruses, and among them certain families like influenza or coronaviruses, are really masters in jumping into new species. It can go in all directions. It can go between animals, it can come to us, we can give our pathogens back to animals, and we also have to say that we are not really good in entangling this really complex network of interactions. We have to be honest, so far, most of the time we fail. And often we don't even recognize what is happening in animals. So there are many examples. We don't know where SARS-CoV-2 came from, okay, but we don't know where Ebola comes from, and we know this virus since 1976. So somehow we lack a lot of understanding. And then there are also some crucial deciding points. If a pathogen either ends with one unfortunate infected host that dies, but then the pathogen dies with that person, or if that pathogen is able to cause an epidemic or a pandemic. And so why is all of this happening? Why are we seeing this increase? There is sometimes this dramatic misconception that there is an evil virus somewhere hidden deep in a forest, and it takes advantage of a mysterious creature like a bat who comes to our cities and wants to infect us and start a pandemic. That is Hollywood. The reality couldn't be further away. In reality, it is us who is driving these emergence events. Biodiversity loss leads to unstable ecosystems. Human disturbance, climate change will further fuel these trends. They will fuel pathogen spillover. You see an example here of Brazil, how a forest is logged to create meadows or agricultural land. And suddenly you have a formerly pristine ecosystem that is exposed to humans, to their livestock, to their companion animals. And what we are doing here, we are actually creating a highway for pathogens to come to us. The consequences of this are massive. So an epidemic or a pandemic touches every single aspect of our life. Of course, it affects our human health, but it also impacts our economy, our society, and the very fabric of how we live together. And until now, our reaction was always reacting to them, but we are not one step ahead of them. And this is what we really need to do. But there's hope, because the same interconnectedness that makes us vulnerable to pathogens also is an opportunity and offers unprecedented possibilities to better survey and maybe even prevent them. So what can we realistically do in the next 5 years? Delivering cost-effective, rapid, and globally available genome sequences coupled with robust diagnostic testing for humans will be a game changer. There are already examples where this is used. Many outbreaks recently have provided genomes very rapidly, and this offers a lot of opportunities. We can really monitor these pathogens the moment they have spilled over. We can monitor outbreaks in real time. However, the access is uneven. It's often not sustained outside of outbreaks, and this is both a technical and a diplomatic challenge. And because this is also a meeting on diplomacy, there's another aspect I want to mention. So countries need to be open and willing to share this outbreak data. They need to be willing to be transparent, and we must find a way as a global community to incentivize transparency and not penalize or even politicize findings or early reports on outbreaks. We also need to map the viral diversity across all branches of life. So think back of that young medical student that I was. Viruses were for me interesting if they infected humans. Maybe we're interested in them because they infect our companion animals or our livestock, but there's much, much more to it. So in reality, these pathogenic viruses, they are just a tiny fraction of what we call the global virosphere. And if you look at that picture, you see this enormous and interconnected virosphere that infects organisms at all branches of life. So we do not only have viruses that infect mammals, but they can also infect arthropods, all the animal kingdom. They can even infect fungi, plants, and even parasites. And we need to better understand this interconnectedness. And we will also realize that viruses are not only pathogens, but they are actually drivers of ecology and evolution. Sometimes they are even important. They have positive effects. But we only need to understand, this global virosphere to really know and anticipate how viruses evolve, adapt, and interact with their host in our rapidly changing world. But we also need to decipher phenotypes. We cannot only collect sequences. It's like reading a book without really knowing what the words mean. So machine learning and AI can help us to detect patterns in this vast amount of genomic data sets that we are creating. But that's only one part. We still need good biological research because these models and these algorithms are only as good as the data that we feed them. So it means we still need laboratories, experimental virology, experimental infectious diseases. We need interdisciplinary teams between data scientists, biologists, clinicians to make these algorithms make sense. And there's also a second aspect. So we can not only ask how would a pathogen look like with a certain genome, but we could also ask what would a genome look like of a pathogen that is, for example, highly transmissible and highly virulent on the other hand, that really kills a lot of people. Again, so there is a risk to this, and we need to find a global governance how to address these risks that arise from possibilities. So let's look a little further ahead, in 10 years. What is reasonable in 10 years? So we can come up with a global surveillance system of pathogen dynamics in real time. So think of that like a weather forecast for emerging infectious diseases. So all this data that we generate on ecology, on biology, on climate change, on movement of humans, of animals, we can integrate all of that into a model, again, with the help of AI and machine learning, and use this. And maybe we do not even need to survey every single spot in the world. Maybe we can have a flexible system that can be adapted once there is an outbreak, but it needs to be global and we need to implement it. But there's another aspect. So we also need AI-based prediction based on biological data and on anthropic drivers. Because the reason when you think about this picture with the many arrows, it's not only the biology, it's actually also our behavior. And unfortunately, human behavior is not logical. It's sometimes unpredictable, but that's just who we are. And so far, we are not very good at incorporating this human behavior. So humans may panic over an outbreak that poses no risk to them, and on the other hand, they maybe do not take a lot of actions for something that actually poses a risk. And we somehow need to better integrate this human element into our models, because sometimes it is like this famous flutter of a butterfly wing. It's a small, seemingly random event that triggers a chain of reaction and in the end leads to a viral spillover. But let's also be pragmatic. So we will never prevent all emerging infectious diseases. That's why we need to invest in broadly acting antivirals. So these are therapies to treat patients and in vaccines. One famous example that is already a little bit advanced is the so-called pan-influenza vaccine. That means you would have a vaccine that would both protect you against the seasonal influenza, but also against emerging influenza strains. And that might be something to lower our risk for pandemics. On the other hand, no matter how good we are, if people do not want these vaccines, then we can create the perfect vaccine, but we need to have trust in science, we need to have trust in medicine, we need to have good clinical studies, we need to have the infrastructure to study all these tools once an outbreak arises. Now comes the hard part, 25 years from now, but let me try. I think at that time, we could have large data and AI-based forecasting of risk scenarios and prevention strategies. That means we can incorporate all of what I told you in an integrated model that can calculate what-if scenarios, that can look into the future, that can do simulations, what we have to do, what will be the outcome if we take this step or this step. Because the most elegant way to address emerging infectious diseases is to not let them happen in the first place. And for my last anticipation, let me dream a little bit. It's a very positive anticipation. I hope we will be there. But I really dream of a One Health approach. So One Health means that we need to see the health of animals, of plants, of the environment, and of humans as one shared goal. And that will not only address infectious diseases, but many other areas, how we use land, how we produce food, how we mitigate climate change, how we deal with chemical pollution. And to do so, I think we need to align our policies, our science, and our values for this common goal. And then emerging infectious diseases becomes less about surprise, but more about stewardship. So when I started this journey, becoming fascinated about bats and viruses and all the amazing things that are happening of which we don't know of, I never thought how much this topic would affect our world one day. But we have the tools, and we need to realize that emerging infectious diseases are not random acts of nature. They are not a fate against which we are powerless. We have the tools, we have the knowledge, and we can decide. So coming back to my question, yes, we can prepare for novel pathogens to prevent and better respond to future epidemics and pandemics. But we need to invest in this globally, and we need to do it today. Because anticipating the future is not only about predicting it, but it's about shaping it. Thank you.
Thank you very much, Isabella. If you have a question, please raise your hand and we'll bring you the microphone. I get to ask, I have a lot of questions. Bats, let's talk about bats.
Yes.
How do they do? They have this superpower, so bats are exposed to all these viruses, but it doesn't affect them. Do we know why? Is there something we can learn from them?
There are several theories. So first of all, it's the second biggest group of mammals. There are 1,500 species. It's amazing. They occur all over the world, except the Antarctic. And they are very old. So they are many million of years. So they were bats when they were already dinosaurs, or shortly after. So they had a long time to co-evolve with these pathogens. And then bats are a little bit like humans. So they like to travel, they like to hang out with a lot of other individuals. And that is also something that probably makes them a perfect reservoir. So there are these caves that are full of millions of bats. And that's perfect for a virus because it finds a lot of hosts. There's also another theory that they have a very special immune system because of this ability to fly. That is something that is metabolically very challenging, so their immune system needs to be able to deal with certain byproducts like reactive oxygen. So they have a very different immune system to ours, and a side effect may be that they tolerate these viruses.
So basically what you're saying is that counterintuitively in a way, they are a better species at dealing with this because they're exposed to more different environments.
Yes, somehow they have a long co-evolution. And if you think of humans, so it's quite new that we are gathering together in such a large crowd and that we are so global and so mobile. So all these pathogens that always rely on finding a new host, it's quite new for our immune system. So when we were still living in small groups and we're hunters and gatherers, we rarely met other people. And probably these respiratory viruses like flu or coronaviruses, they didn't exist at the time. So we are quite a new host for a lot of pathogens.
We just have to think at a different level, not the level of our lives, but the level of the species. I think we have a question.
Yes, thank you. Thank you for the presentation. I would like to know, knowing that viruses are also trapped in permafrost and in glaciers, wouldn't something basic, if I can say so, fit in the plus 5 years perspective is basically reducing CO2 emissions?
Yes, absolutely. I mean, a lot of it comes down to it. It's not just permafrost, it's also invasive mosquitoes that transmit pathogens. It is something that we see is the change of animal behavior because ecosystem change, animals have to compete about resources, so they may meet species they've never met before. And from the viewpoint of a virus, if I may speak about it like a human, but from the perspective of a pathogen, if the receptors fit and the cell machinery allows to replicate, there's no difference between an animal and a human. So I think the key issue is that climate change is driving so many things that really create this highway of pathogens into the human race. And permafrost is one topic that people are thinking about. Maybe there are old pathogens. We don't know when they were really frozen for thousands of years, if they are still viable, but yes, there is a risk to it. And they're not only viruses, they're bacteria who can form spores, who can live for a very long time.
Our speaker from yesterday who gave us a presentation on fungus.
Thank you. Can I continue from Laurent's question? And it might be quite naive, but how do we know that viruses aren't silent pathogens? So irrespective of however robust an immune system is, they either hide from the genome of their host organism or they themselves sloughed off from it. So is there any evidence of the viral record of having been part of a genome of a bat originally, or is it because they're completely not perceived by the host?
Well, there are differences there. So you do find sick bats, but they seem to be especially good in controlling intracellular pathogens, so intracellular bacteria and viruses, but not so good for extracellular pathogens. So everything that happens outside of the cell, bacterial infection, fungal infection, they are not that good. So they are not unique in every way, but there is one certain aspect that is really very effective, that is very different to our own immune system. And about these hidden pathogens or about this hidden mortality or disease, that's true. I mean, even for us, we are only starting to realize that some pathogens that we thought they do not harm us, like some herpes viruses, they may have some impact on chronic diseases that we did not know before. So there are now amazing studies that, for example, by getting vaccinated against zoster, you can decrease your risk for neurodegenerative disease. Getting vaccinated for flu, you can reduce your risk for certain cardiovascular events. So I think there is still a lot to understand about this pathogen-host interaction. And I think this very simplistic view that we had in the past needs to be revised.
Thanks a lot for the presentation. You said that we don't just need vaccines, people also need to trust science and medicine and actually take the vaccines. So how do we get there? And specifically, what can the scientific community do to increase the trust?
Yeah. So I think we need outreach activities. I think this is a nice example, this event. It's maybe not to the public, but it's to a lot of important people. So I think we need to explain what we are doing, why we are doing it, how we are controlling what we are doing it, why it is safe. I think also that scientists were sometimes not really trained in that. I mean, some of us were really thrown out there, maybe during COVID. Climate scientists, I know they know this since a much longer time. But I think it's something that we are not seeing as our primary goal, which is somehow true. But on the other hand, I mean, we are doing this because we have certain values and for a public good. So I think science communication and outreach activities maybe need to have even a bigger place in universities and in the way also how we assess scientific success, because most of the time this is done on the side and it doesn't have only like positive effects. You get harassment, you are maybe perceived as someone who is looking for the stage. So I think we need to integrate a bit more this science communication and outreach into our scientific values and the way we see ourselves as scientists.
So more scientists and epidemiologists on TikTok. Open your account.
Thanks for your talk. So So you talked a lot about the pathogen side, and I'm wondering actually on the defense side, on the hospice, if there is also breakthrough research on how to improve our immune system so that we can adapt actually, so not prevent, but adapt and react to those potential pandemics in no time.
Well, so I mean, one very good way to adapt our immune system is to get vaccines optimally. I don't know if you're thinking about modifying the human immune system or something like that. So I think what we should think about that as medical progress advances, we have more and more immunocompromised patients. So our population is not the same like it maybe was like 30, 40 years ago. So this is also something that can drive pathogen evolution. So for example, all these new variants that you see for SARS-CoV-2, it's thought that they may have arisen in an immunocompromised patient. So, and we are becoming better at targeting some parts of the immune system and not just shutting everything down. So that might be one aspect. But I think in the end, as I said, the most elegant way is just to lower the risk in the first place and then accept something will happen, but then we will be prepared. And then on the other hand, there are some prime pathogens that we know, influenza, coronaviruses, filoviruses, paramyxo. So it's not like they are, we do not know at all who our enemy is. So we can prepare with these antivirals and anti-vaccines.
One more question here. I was very surprised by the map you showed. I think it's the first time I see someone show a world map, and the least dangerous place on the globe seems to be Australia. Because they had like one virus. Is it because people get eaten by wild animals? They don't have time to get attacked?
Well, I mean, Australia has the advantage that many pathogens are not there, and they're doing a very good job in keeping them
really
out.
Isolated from the rest of the world.
There are also bats. There are pathogens in bats. There were also some outbreaks, but yeah, I mean, and the animals are very different. So yeah.
It was interestingly like left alone in your map. Sir.
Yes, yeah, hello. Thanks so much, very interesting. My name is Yoshi, working for the Gavi, the Vaccine Alliance.
Yes.
Yes. 2 questions. So I'm a little bit confused. What we should be really afraid of, like already existing pathogens that we already know, because these are the major killers, right? Like a TB, malaria.
Yeah.
Or the unknown pathogens. That's one question. And the second is what kind of a partnership should we work on? So you said the role of AI, accelerating discoveries. Is it closer working with the private sector, or is it more like multilateral institutions like CEPI? What kind of partnerships can you think of to accelerate this?
So for the first question, both. I think you cannot say one or the other, but I think you also do not have to decide, because in the end, strengthening health system, giving access to diagnostics, there is a lot of synergy. So if you are well prepared for pathogens that we have already, and you have diagnostic pipelines, you have vaccines, then you are also better prepared for pandemics. So I think it's not one or the other, but it's going in the same direction. And it's true that the big killers are the pathogens that we know already. And I also have to say, many of these tools, we have them. They just do not arrive in the place where we need them. Like Mpox, we have good diagnostic tools, but they are not arriving where the outbreak is taking place. And for the second question, so again, I think it needs all of that. I mean, WHO is really the organization to deal with that. And I think they have done an amazing job during many of these health emergencies. I think they are really one of the only actors who can bring together scientists across the world. Everyone is happy to work for them for free and invest a lot of time. So that is something where I think such a global governance could be, and then it could be, of course, coordinated with the different partners that are in a different topic, like vaccines or therapy or surveillance. But for me, this place would be WHO. Yeah.
I'm going to get to ask the last question, Isabella. We sat next to each other over speakers dinner, so I could ask you the questions that were worrying me. And so, right now, AI is the subject of so many fantasies. By the way, it's also the topic of our 10:15 session here, the future of advanced AI. But there's this idea that with AI, you're going to be able to create viruses. And so I ask you over dinner, and I'd like you to share the answer you gave me. I said, is it really true that I can go and synthesize a virus and destroy the world in 1 hour? And
so, I mean, there was an example of a phage. So that's a virus that infects bacteria that was just recently published, where people could create an artificial genome and bring that to life. And it was actually working against the bacteria that was resistant to antibiotics. And of course, you could also do the same and misuse it for something else. Personally, I think we're not yet there because we still don't really know how different genes translate into phenotypes, or what I just mentioned. And we also have this whole lab pipeline. So you still have to do the wet lab. So you cannot kill the world with a sequence, but you need to create it. And well, not everyone has these skills, but of course you can learn them. So I think we are maybe not there yet, but I think it's definitely a threat for the future. But I also wanted to mention these bioterrorism threats, so they are nothing new. So since many years it is known you could create smallpox by ordering DNA fragments. You don't need AI for that. And we have a lot of really dangerous and nasty pathogens with which you could do a lot of harm, and you don't need AI for that. So I think we should somehow balance. It's not a new threat, but maybe it is upscaled a bit by the use of AI. And I think we should think about it now, when I personally think it's not yet possible. How can we prevent that it will happen one day?
Short answer, it's not that easy to engineer viruses. Fortunately, I came out very reassured from that. Thank you very much. That was Isabella Eckerle.
Thank you.